Good afternoon. Let's start lecture. Okay. Just a reminder that the last quiz number 3. Okay. So we'll have that in the last week. As usual, it's going to be in the tutorial. Okay. It's also open book, open notes. It's going to be on the topic of green theorem that we're going to cover today. So it will be on the question of green theorems. Okay. So let's do a quick review here, and then we'll get on to some interesting topic, which is a curl and a green theorem. This is what we did in our previous lecture. We talked about basically conservative field. Conservative field essentially means it's a field which probably when you take a gradient of scalar function, and you can get a vector field. So that vector field will naturally be a conservative field. And there's this very important theorem called fundamental theorem of calculus for line integral. So this theorem basically says if this vector field is conservative, okay, then when you evaluate a vector line integral at here, then you don't need to carry out the calculation. Yes. Pardon me? Yeah, everything after midterm will be part of the final. Yeah. Well, technically speaking, it's comprehensive, so everything you learned before the final, right? You will still have to know them in order to apply all those things. Yeah. Okay. So if you're required to evaluate the scalar line integral here, vector line integral at here, okay, then you don't need to compute this vector line integral. You can use this theorem, basically use the final value of this potential function minus the initial value of the potential function. Then you get these results. Okay? Yeah. Now every year I will test this fundamental theorem of calculus in the final exam, but you don't know. Okay? So you don't know. I wouldn't specifically say that use fundamental theorem of calculus to calculate this question, right? So how do you know? You only know that if this function here, if this vector field here is a conservative field, then you use this fundamental theorem for vector line integral. Okay, and often in time, if you're asked to evaluate this, you actually just couldn't calculate it. You just couldn't finish this. Basically, that means something is wrong. Then you probably had to consider this one here. So sometimes you can't even compute this integral right here. It's just too difficult. But using this fundamental theorem calculus, then you will. Okay, you will be able to finish it. And there are 4 properties that are equivalent, basically all about the conservative field. So you can take a look at this. Right? So conservative field, if you do an integral, it's path independent. If it's if the trajectory is curve C is closed into 0, right? And for conservative field, it had to have a potential function small f, right? And there's an equivalency of doing this scalar line integral. Basically, either you use the original functions f, or you can use this potential function f right here. Okay. Okay. So a question that here first, what we ask it here is actually I read the question. How do we check, right, if a given vector field f is conservative or not? So, if you're given a vector field and then you look at it by observation and you find, oh look, this vector field comes from a gradient of a certain scalar function. You find that gradient function, then problem solved. You know it's conservative. But sometimes it's not so intuitive. It's not so straightforward. You can identify this as a potential function directly. So we need a more systematic approach to check this vector field whether it's conservative or not. So I'll write down the theorem at here, okay? And so we'll go from here, okay? So first for some preamble basic conditions for a domain. Okay, so if you are giving a 2D field or 3D field, there's always a domain, right? For a domain that is basically so-called, this part here is very mathematical. Really, it doesn't really help us a lot, but just to be more rigorous in terms of theorem, so I'll just write it down here. Okay, for a domain that is simply connected, and this function f's component, okay, are continuous. Okay, yeah. So, for example, if you have a vector field, you say, okay, so this is the limited. This is the range. This is basically the region for the vector field I'm studying at. Okay. So for a domain that is simply connected, this is a very mathematical word. Simply connected basically means not a twisted type of a domain, right? It's like, for example, sphere. That's a simply connected type of domain. And the function f, right? This is basically vector function f. Vector function f, as we said, if I use a 3D as an illustration, so this is your function f, right? There are 3 components. So m, n, p. Okay, so there are 3 components for this vector function, and each one of the components are continuous within that domain. So continuous basically means if you plug in x, y, z from the domain into these components here, 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 okay, and they are supposed to be continuous value, not anything like all of a sudden there's infinite or negative infinite, that type of things. Okay. Okay. Then f is conservative if and only if this expression equal to 0. So this is basically the key part of the theorem here. If you don't have to remember all of the other things here, because we will typically deal with the simply connected and the continuous components. So if and only if this cross product equal to 0, then this vector field is conservative. Okay, so that's the checking condition. Okay, that's checking condition in here. So we'll explain a little bit more in here. So if I look at this cross product here, right? First of all, this symbol, okay, we see that before, right? This symbol here, where do we see it? This is called, what symbol do we call it again? Del, right? Gradient. So this guy here, if you recall that, it's basically, it's a vector, okay? It's a vector operator, okay? It's a derivative operator, but it's in a vector sense, okay? So that's your del. And this f, right, as usual, you have m, n, p. Okay, that's your vector field. Okay, that's your vector field. So now we're looking at the cross product between this del operator and this vector field f. So that del cross f, okay, we can just write it as the usual cross product formula. First row ijk, second row is the del vector, which is partial x, partial y, and partial z. Okay. So that's your del operator. Last row is your vector field component, m, n, p. So you have a 3x3 matrix. Okay. Then you calculate the determinant of a 3x3 matrix. Then we get this cross product. Okay, as what we did in many other questions here. So if I calculate this cross product, the determinant here, so the results of this one here is partial p over partial y, partial n, partial z, okay, partial m, partial z, okay, partial p, partial x, So that's the results of this determinant of the 3 by 3 matrix. Right? So that's what basically what del cross F gave us. So remember the journey of the calculus, right? I said from your straight t to partial d to the del, and then at this del location right here we have a del g, and now you see del cross F. Okay, so this little del symbol, we can use it in two different ways now. One is apply it directly to a scalar function. Another one, let's just del F maybe. Another one, you apply it using a vector across it. Okay, cross product with a vector field. And next lecture, or maybe actually probably the last lecture, we have the last one, which is del dot a vector field. So that's basically will be the end of the journey here. Okay, yeah. So this is your del cross F. Basically, what this theory says: if this del cross F equal to 0, then the vector field is a conservative field. Or the other way around, if the vector field is a conservative field, then the del cross F, the vector field, must be 0, right? Must be 0. So you can let it equal to 0. You can let it equal to 0, basically meaning if this is 0, meaning what? Each one of the components at here will be 0. So you end up with partial p over partial y, partial n, partial z equal to 0, or just simply partial p equal to partial n over z, and partial n, partial z equal to partial p, partial x, and then last one is this. Right. So that's equivalent of checking whether the field is conservative or not. Okay, if it's conservative, just check the equality of the three expressions here. If they're the same, conservative. Okay, if it's a conservative field, then they must be the same. So that's basically what this logic says here. Okay, yeah. Now, before I move on to here, because we're going to cover a concept called the curl. So this thing here, okay, this del cross F, is basically, we're going to look at the detail here. It's also called the curl F. Okay, it's called curl F. Mathematically, you can see this is the curl operation on the vector field F. So you can simply just say it's a curl F. Okay, you can see basically curl F. And the last one here, okay, the last one here, okay, which we're going to cover in next week. So this is called a divergence. So this is called a divergence, or sometimes we call it DIVF. Okay, DIVF. Just bear in mind of this in here. Okay. So we're going to look at a curl here, but for now, right? This is basically how you check whether a vector field is conservative or not. Okay. Yeah. I will use an example here to illustrate this example, this theory. Now, in terms of the proof of the theory, and I want you to look at my lecture notes and also look at the textbook. It's a fairly lengthy proof. There are two parts involved, two steps involved in terms of proving this theory. I think it's out of scope for this lecture now, so you can take a look at the lecture notes or the textbook if you're interested in the proof. Okay? Yeah. So let's look at the simple application. Okay, how do we check a vector field whether it's conservative or not? Okay, here's a vector field, so 2D field. Okay, so a little bit simpler. Okay, there's no z component. So the first question is it conservative? So we're going to use the theorem that we just learned here to check this vector field whether it's conservative or not. Okay. Yeah. So what do? We basically first let's nail down
each one of the component at here. So this is your m, this is your n at here, and apparently the p will be 0, right? And m and n, okay, because of 2D, they are just a function of x and y variables now instead of x, y, z. Alright, so now I'm ready to apply my theorem now. So del cross f, okay, is what we're gonna check. So del cross f I j k, and then partial x, partial y, partial z. Okay, that's your second row. And third row, here's your m, here's your n, and p is 0, so you basically put a 0 at here. Right. That's the cross product. And then you can calculate the determinant of this 3 by 3 matrix. As you can see, if p is 0, which is this element is 0 at here, okay, and also the function m and n, they are not function of z, right? They're only function of x and y. So basically, when you apply the result, you can use the formula right here, and the first term, the first two terms are actually 0. So this is 0 here, 0 right here. You will only have this guy left here, only this one, because m is not a function of z, n is not a function of z, and the p function is 0. So the first two terms, they're all 0, right? So you only have the last term here. So the last term, which is partial n over partial x minus partial m partial y k hat. Okay? So interestingly, so you see, when you have a 2D vector field, right, and you use this del cross f, okay, you basically get a vector pointing in the z-axis direction. Okay? So I know what the m and n's are, so there's m and n, so we can simply substitute, we can calculate each one of us. Take a look at what the partial n over partial x is. So here's partial n over partial x, is your n here. You treat the y as if it's constant. So partial n over partial x, 12xy minus, what's this? 3y squared, right? Okay. And then you have partial m over partial y, which is over here. Treat the x as a constant. So 6. What's that? Treat 6. What did I do? 6. Partial. Yeah, that's right. Treat the x as constant, so that you get 12xy. So then you have here what, 3y squared, right? Okay. So apparently, you see these two terms are identical, the same thing. So basically, you end up with a 0 at here, right? Or 0 k hat. Okay. So if this is 0, then that proves this vector field f is a conservative field. Okay. It's a conservative field. So thus this one is conservative. Okay. So if it is conservative, then if you are required to evaluate any vector line integral within this field, you actually can skip the calculation of the line integral. You can use the fundamental theorem of calculus, right? Okay. A natural question from here would be, okay, if this is a conservative, now if you remember, for any conservative field, then this vector field, okay, must have a potential function, small f. When you use the gradient operator to the potential function, you calculate the gradient vector, then you get this conservative field vector f here. Okay, so basically there must be a potential function, small f, such that f equal to del f. Okay, so that's basically the logic at it here. If it is a conservative field, then there must be a potential function f. Okay, so for example, if f here, of course, is going to be f of xy, then you take the gradient of that, then you get this vector field. So the question, of course, here is, so then what's this f of xy then? How do I get that potential function f? Okay, yeah. So that's the second step now. You prove that it's conservative. How do I find this potential function small f? Okay, based on the given condition in here. All right. Yeah. Okay. So this is basically the next step right here. We're going to try to find this scalar function f right here. Okay. Any questions? Okay. Good. Okay. So how do we proceed from here? Right. So we still start from here. Okay, so this is what we know. Okay, we just don't know what the small f is yet, but we do know that the vector field comes from del f, and what that means is, okay, so f function equal to m n, okay, and this del f equal to partial f partial x partial f partial y, right? Okay, now if these two are the same, basically means this m function gotta be this partial f partial x, and the n function has to be partial f partial y. Okay. So this is our starting point, and these two conditions that are here are what we try to work on it here to find out the small function, the potential function f at here. All right. Yeah. Okay. So let's starting from one expression first. Okay. So I'm gonna rewrite this partial f over partial x equal to the m function. Okay. So write it like this. M function, you know that, right? Because this question is given. Here is a vector field f. Here's your vector field has. So this is your m of x, y here. So that we know this. So we know this one here equal to 6xy squared minus y cubed. Okay, minus y cubed. That's your m of x, y. And this is your partial f over partial x at here. Okay. So if I give you a question like this, if I say, okay, df over dx equal to x squared, how do you find out this f function here? You integrate, right? Okay, so you integrate, basically what you do is df equal to x squared dx, and then you integrate both sides, then you get this is f here, you get 1/3 x cubed. Okay, so that's how you do to find out this basically the function f at here. Okay. Now, this is actually no difference from that simple question at here. So what we have here is partial f over partial x equal to this whole chunk at here, right? So what we can do is, let's just integrate both sides. Okay, integrate both sides. Integrate both sides with respect to which variable? To the x. Okay, with respect to x at here. Okay, it's like you multiply this, make this side like a dx at here, right? It's like making this side dx. Okay, and then here that x is gone. Okay, you integrate both sides. If you do this, then you get back this f of xy, right, on the left side. And when you integrate the whole right side, so integrate the whole right side here, you integrate with respect to the dx at here, right? You back to the dx. Okay. However, okay, and another thing that you have to be careful is, okay, so you see, for function single variable, when we integrate both sides, this is basically an indefinite integral. So technically speaking, I should add a what? I should add a constant, right? So if I integrate both sides, then technically speaking, I should add, what should I add? Constant? However, this is a tricky part here. You are integrating with respect to x, but there's another variable, which is what? The y. What are you treating the y as? You're treating the y as if it's a constant. So you're not going to plus a constant c here. You're going to plus a function of y added here. Okay? Why? Because you see here, the idea is you take the derivative of this, then you get back to the x squared, isn't it, right? Okay? Same at here. The idea is you take the partial derivative of this with respect to x, then you're supposed to get back to which one? To this one here. And this is a function of y. So when you have a function y, partial derivative of that with respect to x, it goes to what? To 0, right? So that's why you add not a constant, but you add a function of y added here. That we will figure out. Okay? Yeah. So that's the step added here, right? So you add a function of y. So the first integral is very easy because you're going to integrate with respect to x only, and you treat the y as a constant. So the integral of this, that should give you 3x squared y squared minus x cubed, okay, and plus r of y. Okay. So here's your f of x y potential function. It's not all finished yet, right? There's still one piece of puzzle. This r of y needs to be figured out. But we're almost there because we figured out a good chunk of that already. And by using the first condition, by using this available condition here. And we have another condition we haven't made use yet, which is this one here, right? So we haven't made use of this condition yet. So we're going to make use of this condition, okay, to figure out this r of y at here. Okay. So what's the other condition? The other condition is partial f over partial y equal to n, and n equal to 6 square y minus 3xy squared. Okay, this is the second condition. Okay, so this is your second condition. So the second condition, how do I make use of it? I need to use the results that we just obtained by using the first available condition, which is this the result set here. Okay, that's the results. Here is your f of x, y. Okay. So we substitute this function, okay, the results into this partial derivative. Okay, so substitute this one into this partial derivative. So let's see what happens if I do the substitution. So partial this over partial y, substitute, so 3x squared y squared minus x y cubed plus r of y, right? Substitute into this function f, and this one's supposed to be 6x squared y minus 3xy squared. Okay, so let's look at the left side of here. I'm going to take a partial derivative for each term now. Take a partial derivative for each term. The partial derivative first term respect to y, you get 6x squared y. Second one here, 3xy squared. And then partial derivative this one with respect to y. But this is only a function of y, right? So it's not really a partial derivative anymore. This is basically what? A straight derivative. So you can maybe just call it r prime, right? That's a straight derivative, not a partial. And then this equal to, again, the right side. Okay. Now you compare this left and right. and it's so clear that you cancel these two terms, and you're left with r prime y equal to 0. So what does r prime y equal to 0 means? So this function of y, r of y, it got to be what? Y? It got to be a constant. Now this time it's constant now, right? Now this is a constant here, constant value. Okay? Because derivative constant equal to 0. So basically you replace this results back to the f of x, y. So we say, okay, so your potential function f of x, y is equal to 3x squared y squared minus xy cubed plus a constant c. Okay, constant c. Is that good? Last step, usually, if you're not so confident about your computation, you can always try to verify. Verify to take the two partial derivative, right? To check, is it question mark equal to m or not, equal to n or not. Okay. So that's what we generally, if you've got time, okay, do last step of verification, right? Okay. Yeah. Okay. So this is a typical procedure, very standard procedure, okay, to find out the potential function when you know that the vector field is conservative. Okay. Now, this is example here is for a vector field which is a 2D field, right? 2D at here. If you have a 3D field, so basically there will be a some kind of a function p at here now, right? Okay. And if you wanted to do the same thing, if you're required to do the same thing to find a potential function for that vector field, then you actually will go through the same procedure, but you might actually go through 3 steps at here, okay, instead of just 2 steps. Is that good? Yeah. So, the one assignment question will be just like that. Okay. If I got a question, if I got a little bit of time at the end of the lecture, I will just quickly illustrate a possible scenario for that one. Okay. Any questions so far in terms of how to check vector field is a conservative or not, and how to back derive this potential function from the given vector, conservative vector field? Okay. That's the procedure here. Okay. And this is a very important part of the lecture, so I typically will also test this with in the final exam here. Okay, so just make sure you understand the procedures correctly. Okay, so let's go back to this curl at here. Okay, so as we learned, okay, and I already showed you already, this is basically curl. And we use this symbol right here. So now it's time for me to explain this a little bit, okay? And in terms of the meaning of a curl, because the computation of the curl, as you see, it's actually very easy, right? The computation of the curl is basically the determinant of this 3×3 matrix. Yeah, Dan.
So if we have our m component with something like x plus y divided by z, we don't even need to do the cross product, right? Because it's not continuous.
Come again? If you have...
Or m is something like x plus y divided by z. It's not continuous.
Right.
We need to do the cross product, right?
Good point. Yeah. So it's basically boils down to the nitty-gritty definition on the conservative of the fields or not, right? So I'll give you one actually example. Maybe let me see. I will give you one example here. Maybe okay. Well, I'll just write it down. We'll look at this a little bit again here. So let's see if I have vector fields like this. Okay? Yeah, very similar to what you said divided by z, right? Here is divided by x squared plus y squared. So technically speaking, when you look at this vector field, and if you go ahead and you check this one, okay, you go ahead, you check this, and you actually will find it out this is equal to 0. Okay? Yeah. Now you may draw a conclusion that this is a conservative field, isn't it, right? But now if you actually look at the nitty-gritties of the definition, I wrote it down here. What did I wrote it down at the beginning? This is basically the cover my alright. So for a domain that is openly simply connected and that the f's of component are continuous in the domain. So this function at here, right? This 0, 0, that location, okay, doesn't give you the continuous one. So if your domain really includes that origin 0, 0, then this is not a conservative. This is actually not a conservative field. Okay, yeah. So you don't have to worry. Actually, I usually wouldn't trick you like this in the example. But this is a really complete understanding of the definitions of a conservativity of the vector fields. Okay, yeah. So typically you just check whether it's 0 or not. That should cover most of the cases that we're dealing with. Okay, yeah. So let's get back to the curl, huh? Yeah, I will go back to this vector field again, but let's go back to the curl right here. Okay. Now this is the curl. Okay, and in terms of computation, as I said, it's not too bad. You know, just the cross product of determinant cross product and determinant of a 3x3 matrix. Okay, yeah, that's curl. But what exactly is a curl then, right? What's the interpretation of the curl? So let me start with maybe a simple example right here. Okay. So I'm going to bring this one into my alright. Okay, so let's see, for example, right? I have a vector field. So this is the vector field v equal to e to the power of a negative y squared over 8I hat. Alright? Yeah. And the red one here is a sketch of this vector field. Okay, so if you look at this vector field at here, now did you look at the arrows, okay, representing these vector fields? What does it remind you? It looks very much like a what? Like a flow of a river, right? Flow of a river here. So if you look at observe the flow of the river, and it's typically in the center of the river, the flow faster, and is approaching the bank of the river, and the flow is slower, right? Okay, yeah. Now this is actually a so-called, basically a shear flow. Okay, it's a shear flow. Okay, if you go to the fluid mechanics, okay, this is one type of a field called shear flow. So imagine what's going to happen now if you toss a stick into this river. Okay, put a stick here or here. So what do you think the stick will do? It'll spin, right, or rotate. Okay, yeah. Now if I put it on the top of it here, it tends to rotate which direction, as you can imagine? Good. If I put it at the bottom here, right, the clockwise. Okay. So basically, if you put something into a field, okay, if you look at this river here, it doesn't appear to be any rotation, right? But if you put something there, there's a tendency to cause a rotation at a certain point. Okay, yeah. Now that's basically what we're trying to grasp, or trying to extract the information out of this vector field here. It's about the circulation. So rotation, we can call it circulation. It's about the circulation at a certain point inside a vector field, right? Yeah. And then also, I can use an example. If you're a weatherman, then you want to predict or forecast the wind speed, right, of today's weather. So what do? You basically hold a paddle wheel, right, inside the air or somewhere, okay, and then you look at the spinning of this paddle wheel, and you can tell, okay, so today the wind speed like this, okay, yeah. But I don't know if you noticed or not, if you hold a paddle wheel this way or this way or this way, And guess what? They turn at different speed, isn't it, right? They turn at different speed. So that's an information basically also tells us at one location, if you orient it to a different direction, it gives us actually a different type of circulation information, right? And that's also something we want to extract from this vector field. And this is everything can be extracted from this operation del cross f, right? So I'll go into details of it here, okay? And we'll look at the definition of this curl a little bit more, okay? Not just the computation. Okay, so also recall, okay, if we have a closed curve C, okay, if I have a closed curve C and a vector field F, okay, then we have done this quite a bit. So we've done this f dot ds, this vector line integral, right? So vector line integral has a different way of writing it. Okay, so these are all the same formula. Okay, these are all the same formula. Okay. So you have a closed curve C, and then you integrate this vector field across this curve C. Okay. So particularly the second one here, as we teach this one here, and I don't know if you remember, the second one here is f dot t hat. T hat is the tangent vector, right? So the direction of the curve C. So any vector dot unit vector, the projection. So this is the projection of f in the direction of curve C, right? And then you integrate this one across the whole curve C. So you're adding basically all the projection of the f into this t hat direction. You add them up, you get the total circulation. So this essentially, if you recall that, right, this is called the circulation around curve C, right? Around the curve C. Okay. So now I'm gonna illustrate this curl it here, okay? Like this concept here. Let's say I have put it in a 3D perspective, okay? Put in 3D perspective, and we have a vector field, okay? Not sure how they look like, but there are definitely certain distribution of the vectors in this field at here, okay? So what we're gonna do is we're gonna pick a small area, okay? We're gonna pick very small area encircled by a curve C. So this is your curve C at here. And this curve C, okay, so small, okay, and there is an orientation associated with it. So that right hand rule, okay, supposed to give me a perpendicular vector over here. So let's call it n hat. Okay, so that's n hat. Okay, so n hat is perpendicular to the area, okay, enclosed by curve C. Okay, so that's the relationship between this n hat and the curve C at here. So curve C encloses a certain area. So let's call this delta A here. Okay, this is your delta A is the area. Enclosed by C. So now you can imagine you have a curve C delta A like this, right? If I orient the curve C differently, so I get another small area. Differently, another small area. The magnitude maybe is the same, but they orient all to a different direction, right? Orient to a different direction here. So I might as well define a vector, okay, representing this small area. So this delta A vector here. So delta A vector has a magnitude, which is delta A. and it has a direction. I'll use which direction? I'll use this n hat, okay, representing its direction. Does that make sense? Yeah. So this has actually become a norm from now on. So when you have a small area, there are two information. It's actually a vector. One is its magnitude, and the other is its orientation. The orientation is a vector perpendicular to this small area. All right? Yeah. So that's basically what I'm looking at here now. So then the question at here basically is, okay, so I'm looking at this one here. What will be the circulation information, okay, around this small area, okay, enclosed by the curve C? Okay. So that's essentially the idea I was trying to illustrate. Now you hold it to a different direction, the pedal wheel, right, pointing in a different direction, and you get a different type of circulation information, right? Yeah. So that could be explained if I look into the details, which is described by a small area like what I showed it here. All right? Yeah. Okay. So, and now we're going to define something at here now. Okay. So here I'm going to take a circulation. Okay. I'll take the vector line integral. Vector line integral right here. Okay. Take the vector line integral across this small curve C. So that's a circulation, right? Circulation around the curve C. And then we're going to use this value divide by the small area enclosed by curve C. Okay? Yeah. Is that good? Yeah. So this one at here, okay? Use a different. So what's mass divided by volume? Density, right? Or mass density. So what do I do here is what? I have a circulation over the curve C divided by the area enclosed by the curve C. So this one here has a meaning. It's also density meaning, but this is called circulation density. Okay, this one here is called circulation density. Okay, more precisely, you see, the top one, the numerator is the circulation. The denominator is the area. So we can call this is basically circulation per unit area. So that's basically a density concept. It's like a mass per unit volume, right? Here is a circulation per unit area. Is that good? Okay. So we don't stop at it here actually, okay? But you know, density is always not just a general, it's a small area property. When you say density, it's actually a point property. You know, okay, at that point you have this much density. At the other point, and you have that much of a density, right? So what we do from here is we actually take a limit for this expression. Okay, we take a limit for this expression, and we let this small area delta A go to 0. Okay, so you have this basically starting from the curve C with the n hat, and then you let this area go back to 0. Okay, it's infinitesimal small. So that's what happens at here. Okay. So what this one gives, okay, is basically circulation density at a point. Okay, circulation density at the point. And more precisely, I think I should put in the n hat direction. Okay, in n hat, because this is a certain orientation, n hat orientation, because that's C, right? Enclosing this delta A, the C, okay, has n hat normal vector. And this limit set here, okay, is directly related to the curl. So how does it relate it? It's basically related like this. So curl F dot n hat okay, equal this limit. Okay, it equals this limit. Is that good? Yeah. So the rest of the work, let's just look at this expression a little bit again, and to look at the meaning of the kernel. If a circulation density is equal to 0, guess what's going to happen if you put something over there, the paddle wheel, at the location? Will it rotate? No, right? So the circulation density is a quantity to tell us the rotational information at that point in a certain direction of this n hat, okay, the n hat direction. But now you see, this circulation density definition is directly related to the curl f dot n hat. What is the dot product again? When you use a vector, dot a vector, meaning what? Projection, right? So basically here, this one yields a vector, okay? This yields a vector here. And that vector project onto the n hat direction. What does that give us? Give us the circulation density, right, for this point in that direction. Is that okay? So now if you extract this out, right, just look at this curl f. It has a magnitude. It has a direction. Okay? It has a magnitude. It has a direction. What does the magnitude give? What does this direction of this vector give us? So coming back to here, this dot n hat gives this. When you use a vector dot n hat, under what condition that you will have the maximum value? Under what condition that this dot product is the maximum? They're parallel, or they are the same direction, right? So basically means if n hat is in the same direction as curl f, we get what? A maximum, what quantity? Circulation density, right? So if n hat is same direction as curl f, okay, so max circulation density, okay. And what's the value of the maximum circulation density? It's the magnitude, right? It's the magnitude, okay. So now coming back to the paddle wheel question. If you want to give people the maximum wind speed, okay, if you want to give people the maximum wind speed currently outside the classroom, how would you hold your paddle wheel? You had to hold your paddle wheel the same direction as what? Huh? Same direction as the this. That makes sense? Right? So of course you have to calculate the curl f first, right? And you do curl calculate, you need to know the vector field. But often in time you can try it out, you know, okay, so that must be the maximum here, right? Okay? So what the curl f now, you see, basically what it tells us is all about the circulation or the rotational information at a certain point. The magnitude gives us the maximum rotation, okay, the maximum rotational or speed, okay. Okay. And the direction give us which direction has the maximum, basically, which direction has the maximum rotation, right? Okay. So what the curl basically means at here. The magnitude, okay, gives the absolute value, okay, of the maximum rotation. The direction give us on the direction you have the maximum rotation for that vector field. Okay, yeah. So a number of things, you know, if you are going to remember for the course, you know, I think I told you one already, which is what the gradient of a function means, right? And here another one. What does a curl of a vector field means? Okay. The physical meaning of this. And the last one, which is a divergent. What does a divergent of a vector field means? So these three things is essentially the essence of this course. Okay, yeah. You can forget about everything, but if you can remember these things here, these three things, okay, and you pretty much remembered everything. Okay. So, any questions on the curl? Computation-wise, I don't see any problem. It's just a cross product. It's all about interpretation, right? And if you can, interpretation can be directly remembered or interpreted from this definition, the formula at here. So curl dot n hat equal to this. Okay. There are a little bit details, okay, in terms of each one of the symbol, but everything can be explained from here. Okay. A number of I guess I don't have to write it here, but we can use an example here to illustrate the idea here. Okay. Yeah. So let's look at one example quickly here. Alright, so let's say I have a flow of a fluid, okay, which is rotating around the z-axis, okay, all at constant velocity, angular speed omega at here. Okay, so all of them are flowing at the counterclockwise direction with angular speed omega. So basically omega, okay, is in the z-axis like this. Okay, yeah. Now I can easily derive, okay, the velocity field, okay, because the flow of the fluid at here. So to derive the velocity field, we can grab a whole bunch of position points inside this field. So this is a position field here. Then we can basically sketch or calculate. I'll show you how to calculate. We can sketch out this velocity field, okay, because it's flowing, right? The velocity basically indicates the direction of flowing, and it's tangent to the circle right here, of course. So that's your velocity field. Okay, so let's calculate the velocity field first, okay, and then let's calculate the curl at here, and I'll explain a little more on the curl again. Okay, so first of all, to calculate the velocity field, we start from the position vector. Okay, position vector. Now, position vector describes the trajectory of the flow. So if you look at the trajectory at any point, it always flows in a circular trajectory, right? So it flows at a certain radius with, okay, certain angular change. So and that's basically your position vector. Okay, position vector here. As we can easily see in this question, your theta dot basically is the angular speed omega. Okay, so theta dot will be this. And position, when you look at one particular point, the r always rotates at a constant radius. So your r dot will be 0. Okay, so the derivative r dot will be 0. Now velocity vector is the derivative of the position vector. or dr over dt. Okay, yeah, dr over dt. So here's your r. Okay, so we can calculate the dr over dt. Okay, by using product rule. Basically, you have a r, you have a theta, then you can calculate using product rule. But r dot is 0, so overall, okay, you get cosine theta, you get a negative theta dot sine theta, okay, I hat, and plus theta dot cosine theta j hat. Okay, yeah, and theta dot is omega, so this is basically, you can take the omega out of this bracket and move the r back into the bracket. Okay, yeah. So that's your velocity field. And then a little bit simplification, because r sine theta is y, r cosine theta is x. There we go. So your velocity field is this one. Okay, so this is your velocity field. If you sketch it out, it's exactly what I just showed you at here. Okay, and that's your velocity field. Okay, this is v here. As it's getting out further away from the origin, you get a faster velocity for the flow. Okay. Oh. Okay. So I got the velocity field now. Okay. And let's calculate the curl of this velocity field. Okay, let's calculate this curl of the velocity field here. Basically, it's the cross product, del cross f. Okay, yeah, very easy. You plug it into the cross product formula. Okay, and here's a vector field. You're gonna end up with a 2 omega k hat. Okay, 2 omega k hat. Is that good? Okay. So you look at the results of the curl f here. First of all, which direction is it pointing to? Pointing to the z-axis, right? And what's the magnitude of this vector here? 2 omega. And what is the angular velocity speed of the whole flow, which is what? Omega. So this is basically twice as much as that flow of the velocity, right? The angular speed. So what does this one give us? But you remember, what does this one give us at here? This is the circulation at a point. Okay, this is the circulation at a point location. But it just happened that if you pick any point, okay, if you pick a point over here, pick a point over here, 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 doesn't matter which point you pick. You pick a point right there, and what would you expect? You would expect there will be a rotation at that point with how much? With a 2 omega. Okay? So imagine what's going to happen now. If I have a ball, okay, if I got, now this is actually what I show you. If I place a ball somewhere here, okay, if I place a ball somewhere here, what type of a motion would you anticipate this ball to go? It'll go around the z-axis, right? With what speed? Omega. And at the same time, the ball will do what? Self-rotation with what speed? 2 omega. Okay. So the curl dot f, if I give you an example with it here. So this is an illustration of not necessarily that field, but you see this ball here, right, is rotating around the z-axis, but at the same time it's also doing self-rotating. That self-rotating is described by the curl f calculation. Okay, so the curl f at here, what is it called? So this curl F give us the so-called microscopic okay. Microscopic basically means the point information. Okay, at that point, microscopic. How does it rotate? Okay, how does it rotate? Now, if you get the curl F equal to 0, okay, sometimes you calculate this, you get equal to 0 at a certain point, right? Or maybe you get a 0 at any point. Okay, in general, you get a vector field, you calculate the curl F, you end up with a 0, which is actually for conservative field, that's basically what it is, right? Now this one, if this is the case here, and we actually call that irrotational field. Okay, irrotational field. So what's the meaning of irrotational field here? So I'll give you another example, which is actually I wrote it down in order to answer Dan's question there. So let's say that vector field V, as I gave it to you previously. Okay. So if we have this vector field, and you can calculate this vector field, and you'll get del cross F equal to 0. Okay. It's not a conservative, but this is not a conservative field. Outside the origin, they're still conservative, but if origin is included, then it's not conservative. But this del cross product is 0. Now, if this is 0 here, then if I place a ball right inside this vector field, okay, so this is basically what happened to the ball. You look, watch the ball there. The ball will rotate around the z-axis, but the ball itself, look at that. Does it have any self-rotation? No, right? Yeah. So this is basically the difference between microscopic rotation, circulation, and the macroscopic, okay, circulation or rotation. Okay. So the key words here is the microscopic for the curl, okay, but don't mix with this macroscopic. Okay, the macroscopic rotation or circulation. There is a connection between these two, though. Okay, at the end of the lecture, we will learn the so-called Stokes theorem, and that's going to connect this microscopic with this macroscopic circulation. Okay. Is that good? Yeah. So now, in terms of curl, if I wanted to use one sentence to summarize, so curl describes a circulation information at a point, okay, and it's a microscopic circulation, okay, for a vector field. That's basically what it is. Okay? Yeah. Any questions? Okay. Okay. So last topic, green theorem. Okay, green theorem. It is a theorem. It's actually in terms of computation. There's nothing we learned before, nothing we have not learned before. Okay, it's just a new theorem, putting things together, right? So when do we use this theorem now? Okay, yeah. Now imagine the situations that we have looked at so far. We look at a general vector line integral. So we have a general vector line integral. So we look at that. Okay, so you need to know the parametric equation for the curve C, and you need to have the vector field, and then we can calculate this vector line integral, right? Okay. And then we look at another special situation, which is what? Which is when the vector field, when the vector field is a conservative field. If it is, if it is conservative field, then if C is closed, then it's near 0. If C is not closed, then you use the fundamental theorem for vector calculus to calculate, right, by finding out the potential function. So here's the third scenario. So the third scenario is, so F is not conservative. Okay? So F is not conservative. And C is Okay, so-called, it's a simply enclosed curve. Okay, C is a simply enclosed curve. Simply enclosed basically means it doesn't have a topology-wise, doesn't have a twisted here and there altogether like that type of curve C. It's maybe just a very simple curve C like this. All right? Yeah. So if it's simply enclosed curve C and C enclosing a region R. Okay, right? So whenever you have a curve C, okay, it's enclosing the curve, give a region R. Now Green theorem, okay, we're focusing on in plane. Okay, so for 3D, so you could have a curve C enclosing R at a different orientations, but that's actually going to be the last part of the Stokes theorem. So here we're going to look at the in plane here for the Green theorem. In plane basically means the curve C, okay, the C is in XY plane. Okay, this is basically what Green theorem will focus on. Okay, it's about a C in XY plane, and region R, of course, is also in XY plane. Okay, that's in plane case. For this situation, right, if we are going to evaluate this vector line integral, and we have an alternative approach given by this Green's theorem, and this is basically could be evaluated by the right side over here. Now this is your Green theorem here. Okay, so it's one formula. Okay, tells you how do you evaluate this vector line integral. But ultimately, it's a connection between what? Between a single integral and a double integral. Okay, a double integral. See, now you see things are starting to put together now. This is basically why I say you have so many things involved for the last few lectures. You look at this one single formula. What does it involve? Dot product, parametric equation, right? And double integral, maybe different type of coordinate system, not necessarily Cartesian coordinate system, partial derivative, right? So a lot of things are putting together at here now, right? So in terms of the evaluation here, it's quite straightforward. You just have to know the R is the region enclosed by the C, and you have to calculate the two partial derivative here. So the F vector field at here is Mn at here. Okay, so this is the idea of this one. Let's take a look at the example here. It should be quite simple, okay, to illustrate. Here's your vector field, and C is x minus 2 squared plus y squared equal to 1. Okay, so here's your C here, and we want to evaluate this vector line integral. All right. And you can certainly evaluate this vector line integral as if the traditional approach, take a parametric equation of the C and then do all of this, right? Replace x, y with the parametric equation, and then you do all of the rest of the work, right? Okay. But I don't want to do that. I want to use the Green's theorem, okay, to do this. Okay, use the Green's theorem, right? If I use Green's theorem, let's see what's going to happen at here. Okay. So here is the Green theorem, right? Now, I have m at here, and we have the n at here. Okay. So we just have to calculate partial n over partial x and partial m over partial y. Okay. So that'll give us one is x plus e to the power negative x. The other one is e to the power negative x at here, and then dx dy. So you'll cancel these two out, which is x dx dy. Okay? Yeah. So that's this double integral. Sorry? Not yet. The region R is, this is your region R, right? Yeah, that's the next question I'm going to deal with this here. Okay? So from here, you actually have two different approaches. I'll show you one, but there's one approach I want you to try yourself. Now, if you starting from here start to evaluate using dx dy, basically find x, y limits, that's fine, right? But a Cartesian, typically it'll be difficult. But if you use a polar, because the circle is not centered at the origin, so it also proved to be actually quite challenging. So what you have to do now is you try to shift this circle back to the origin by doing what? One of the approach we learned. Change of variables. Okay, change of variable. So you can do let u equal to x minus 2 and v equal to y, right? And then you solve for x, solve for y in terms of u and v. If you do this, you're going to shift the circle back to origin. Then you can use the polar coordinates, okay, to calculate this double integral. So I want you to try it yourself, okay? Yeah. But I'll give you a trick at it here for this question. So the trick is, if you recall, the formula for the center of mass is what? Is 1 over the mass and x times the density, then times this dA, right? That's the center of the mass formula for x bar. If your delta x or y equal to 1, then this formula will become, so the mass is double integral delta dA. If delta equal to 1, then the mass calculation is equivalent to calculate what quantity? If delta equal to 1. Not the volume. What? This, the area, right? Area here. So basically, this will be the area here if delta equal to 1. And then here is just x dA at here. Okay? So that formula morph into this if the density equal to 1. Why does it help? Because for this particular example, I'm looking for this value at here, right? So that value is equal to x bar times the area, okay? Times the area. Now for the given region R, for the given this, what's x bar? You don't need to calculate, right? What's x bar here? What's the center mass for the x? 2. And what's the area of this? Pi times r squared, which is pi. So 2 times pi, right? X is 2, area is pi r squared. So the results for this one here is 2 pi. Okay? So that's an alternative approach. It's a little bit tricky, but yeah. If you try change a variable, you'll get the same answer. Okay? Any questions? Yeah. So that's basically about the green theorem. You'll get a chance to practice a few more examples in assignments. Okay? And the next week you'll have a quiz on this green theorem.